This talk deals with some neurophysiology topics that are usually hard to grasp by first and second year medical students. This is the first section in a 4-part series. The section outcomes are listed here. You do not need to read them. They will be covered during the course of this talk. This talk will be conducted in a question and answer format. The first question is, at the equilibrium potential of an ion, the chemical and electrical forces acting upon the ion are in balance. A true, B false. We will answer this question using a mind experiment. With a voltage clamp to manipulate the membrane potential and an ion flow measuring device to determine the net flow of potassium across a membrane. We will conduct the experiment using an axon with an intracellular potassium concentration of 140 millimoles bathed in a fluid with a potassium concentration of 4 millimoles. A voltage clamp to manipulate the membrane potential, and an ion flow measuring device to determine the net flow of potassium across a membrane at different membrane potentials. This arrangement will allow us to determine the equilibrium potential of potassium, that is the membrane potential at which there is no net flow of potassium from the intracellular to the extracellular space or vice versa. This will be done by manipulating the membrane potential while keeping potassium intracellular concentration at 140 and extracellular concentration at 4. We will start by clamping the membrane potential at positive 120, as represented here. At such membrane potential, large amount of potassium would leave the cell, as represented by the thick arrow, and very little would come in, as represented by the thin arrow. Thus, the net flow of potassium is outwards. This is so because the diffusion gradient and the electrical gradient propel potassium out of the cell. If the membrane potential is changed from positive 120 to negative 96, as depicted here, the proportion will change, but the net flow will still be out. If membrane potential is then changed from negative 96 to negative 97, as depicted here, the flow of potassium will be the same in both directions, as represented by the equal thickness of the arrows. Hence, no net flow will occur. This is so because the diffusion and electrical forces acting on the ion are balanced. Hence, at this membrane potential, the membrane has reached its equilibrium potential for potassium in this experiment. So the answer to this question is true. Next question. The terms equilibrium potential and reversal potential of an ion are interchangeable. A true, B false. Using the same example as we used to answer the prior question, in the hypothetical axon we described when the membrane potential was at negative 96, the net flow of potassium was outwards. When the membrane potential was changed from negative 96 to negative 97, potassium flow in both directions equally. When the membrane potential was changed from negative 97 to negative 98, the net flow of potassium was in. It is because of this shift in direction of net flow that the equilibrium potential, in this case negative 97, is often referred to as the reversal potential. So the answer to this question is true. Next question. The equilibrium potential can be calculated using the Nernst equation. A true, B false. The Nernst equation allows us to calculate the equilibrium potential. I think of the Nernst equation as a puzzle that has to be put together a piece at a time in order to solve the equilibrium potential of a given ion. This cartoon, as you recall, was used before to denote that if an ion is pushed by two forces, such as an electrical force and a diffusional force, and both forces are of equal intensity but in opposite direction, there will be no net flow. This concept is expressed mathematically by this simple equation. At equilibrium, the electrical work required to move an ion against a voltage is equal to the diffusion work required for the ion to be moved against this concentration gradient. So the answer to this question is true. Next question. In Nernst equation questions, you are commonly given the intracellular and extracellular concentrations of an ion to find the equilibrium potential of the given ion. A true, B false. Now let's look at the factors involved in electrical work. Electrical work is equal to membrane potential multiplied by Faraday constant multiplied by the valence of the ion in question. Summarizing these points, we can say that electrical work is equal to electromotive force, that is the membrane potential, multiplied by the Faraday constant, multiplied by the valence, which in the case of neurons and muscle is limited to 1 in the case of sodium and potassium, 2 in the case of calcium, and -1 in the case of chloride. So now that we review the factors involved in electrical work, let's look at the factors involved in the work of diffusion. The formula to express the work of diffusion is, as you can see, a bit more complicated than the formula for electrical work. It goes like this. The work of diffusion is equal to the universal gas constant multiplied by temperature multiplied by the natural logarithm of ion concentration outside the cell divided by the natural logarithm of ion concentration inside the cell. Summarizing these points, we can say that the work of diffusion is equal to the universal constant of gas multiplied by temperature in Kelvin multiplied by the natural logarithm of the ratio of ions outside and inside the cell. Now that we have looked at all the pieces of the puzzle separately, we will start putting them together one by one until the puzzle is complete. So we take the initial simple formula and represent each of its factors on the corresponding side of the equation, as you can see here. We then take the elements on the line in red and we arrange them to make it easy to work with them. Now you see a set of elements with red background. We can, by redistributing these elements, construct this new equation in which we have isolated the electromotive force, which corresponds to the Nernst potential. To achieve the isolation of the electromotive force, we have taken F, which stands for Faraday constant, and C, which is the valence of the ion in question, which are multiplying on this side of the equation, and move them as divisors to the other side of the equation. Now we can further simplify this formula. If the temperature used to conduct the experiment is the one corresponding to the normal body temperature, that is, if the temperature used to conduct the experiment is 37 Celsius, by substituting and rearranging the elements with the red background based on standard calculations. As such, this number results from the conversion of natural logarithm to logarithm of 10 and the multiplication of the gas constant by 37 Celsius, the temperature used while conducting the experiment, and dividing the result of this multiplication by the Faraday constant. This sounds confusing, but at the time of solving equations for your exam, only 5 things are important. To memorize the last formula, to have a general idea as to how the formula came about, to remember the number 61.5, to remember the balance of each ion, and the steps you need to solve the equation. The steps needed will be discussed during the next question. So the answer to this question is true. Next question. Solving the Nernst equation to arrive to the equilibrium potential requires 4 steps. A true, B false. To solve this equation, we must first divide the ion concentration outside the cell by the ion concentration inside the cell. The second step is to calculate the log of 10 of the result of the prior division. The third step is to divide 61.5 by the valence of the ion being considered, and the fourth step is to multiply the result of step 2 by the result of step 3. So the answer to this question is true. Next question. In a frog muscle fiber with the ion concentrations shown below, if only sodium channels are open, the calculated Nernst potential is positive 62 millivolts. A true, B false. In this frame, I will introduce several elements corresponding to each of the ions listed. The first row corresponds to their extracellular concentration, the second to their intracellular concentration, the third to their valence, and the fourth to the experimentally measured equilibrium potential. Notice that the ion with the highest measured equilibrium potential is calcium. Now I have introduced the Nernst equation. We will use this equation to determine the equilibrium potassium of sodium. We first divide the concentration of sodium out by sodium in, that is 150 by 15. The result is 10. Next, we figure out the log of 10 of 10, which is 1. Next, we divide 61.5 by the valence of Z, which for sodium is 1, this operation yields 61.5. The last step is to multiply 61.5, the result of the division of 61.5 by 1, by 1, the result of the log of 10. The result is 61.5. This number is the calculated equilibrium potential of sodium, which is about the same as the measured equilibrium potential of sodium in this example. So the answer to this question is true. Next question. In a frog muscle fiber with the ion concentration shown below, if only chloride channels are open, the calculated Nernst potential is negative 97 millivolts. A true, B false. Nernst potential for chloride is gotten by taking the same steps, that is, by dividing the concentration of chloride outside by the concentration of chloride inside, we get 38.33. Then we find the log of 10 of 38.33, which is 1.58. Then we divide 61.5 by negative 1, which is the balance of chloride. This operation yields negative 61.5. Finally, we multiply 1.58 by negative 61.5. The result is negative 97.17. This is the calculated equilibrium potential of chloride, which is about the same as the measured equilibrium potential of chloride in this example. So the answer to this question is true. Next question. Which of the following permeability relation is present in most neurons when the neuronal membrane potential is at rest? A. Potassium 1, sodium 0.04, chloride 0.45. B. Potassium 10, sodium 0.04, chloride 0.45. C. Potassium 1, sodium 20, chloride 0.45. D. Potassium 1, sodium 0.45, chloride 10. In this frame, you can see the membrane voltage in millivolts, the resting membrane potential at negative 70, the Nernst point for potassium at negative 90, the Nernst point of chloride at negative 66, and the Nernst point of sodium at positive 55. Now I have introduced a column with 3 rows to indicate the permeability of potassium, sodium, and chloride. In the second column, you can see 1, 0.4, and 0.45. This relation expresses that for each 100 channels of potassium open, we will have 4 channels of sodium open and 45 channels of chloride open. In such case, the membrane potential will be less negative than the potassium Nernst point because the contribution of chloride and, to a much lesser degree, the contribution of sodium to the membrane potential. This is the numerical relation of channels open that we find in most neurons at rest. In the case that only potassium channels are open, the membrane potential would be at the Nernst point of potassium. If only sodium channels are open, the membrane potential will be at the sodium Nernst potential, that is at positive 55. If only chloride channels are open, then the membrane potential will be at the Nernst point of chloride. If the proportion of open channels is potassium 10, sodium 0.4, and chloride 0.45, the membrane potential will be almost at the Nernst point for potassium, because for each 1000 potassium channels open, 40 channels of sodium will be open and 450 channels of chloride will be open. But if instead the ratio of open channel is 1 for potassium, 20 for sodium, and 0.45 for chloride, then the membrane potential will be close to the sodium Nernst potential. If the proportion of channels open is 1 for potassium, 0.04 for sodium, and 10 for chloride, then the membrane potential will be nearest to the chloride Nernst potential. So the answer to this question is A. Next question. Please view this equation and select the one that is incorrect. The Goldman equation explains how the different ions interact with each other to generate membrane potential at different stages of activation. Hence, unlike the Nernst equation, which deals with one ion at a time, the Goldman equation deals with multiple ions simultaneously. Mercifully, questions about Goldman equation are not frequent in boards. When they are asked, the kern of the question is the arrangement of the different factors. This can be easily solved by paying attention to the first number in the equation. If the first number is negative, the value in the dividend should be intracellular potassium, intracellular sodium, and extracellular chloride. If, on the other hand, the equations start with a positive number, then in the dividend, the arrangement should be extracellular potassium, extracellular sodium, and intracellular chloride. So the answer to this question is C. Next question. All cells have the same membrane resting potentials. A true, B false. Not all cells have the same resting membrane potential. In this frame, I have placed cell type and resting potential as a heading for 2 columns. Most neurons have a resting membrane potential of -70, mammalian skeletal muscles -80, frog skeletal muscle -90, cardiac muscle -80, cardiac Purkinje fibers -90, atrioventricular nodal cells -65, sinoatrial nodal cells -55, smooth muscle cells -55, and human red blood cells -11. Frog skeletal muscle is the most often used model to describe experiments related to the Nernst potential. So the answer to this question is false. Thank you.